Hello everyone. The title of this video is Using Like Bases to Solve Exponential Equations. In this video, I'm going to be doing examples that are taken directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text, section 6.6, called Exponential and Logarithmic Equations, and I'm under the heading Using Like Bases to Solve Exponential Equations. Alright, what we're going to be doing in this video is making use of the one-to-one property of exponential functions, which I'm going to read to you here. So for any algebraic expressions s and t, and any positive real number b that's not 1, b to the s equals b to the t if and only if, right? So this means this goes in both directions. S equals t. Right, and this is because exponential functions are one-to-one functions, right? They pass that horizontal line test. Two different inputs are going to give you two different outputs. That's where this is all coming from. So if we have an equation where both sides are a single base to a power, and that base is the same, this tells us that the powers must be the same as well. And they go through a little how-to here, right? You're going to be using properties of exponents, rules of exponents, to get an equation to look like this if you can, where you have b to the s equals b to the t, both sides with the same base, and then you apply this one-to-one property to set the exponents equal and solve the resulting equation and check your solutions, of course. Alright, so let me get into some examples. And each example is taken directly from the reading or one of those try it problems or one of the exercises at the end of the section that's related to this objective. Alright, so using like bases to solve exponential equations. Now the first example I have here, we're asked to solve 2 to the x minus 1 power equals 2 to the 2x minus 4 power. Both of these are already written in that fashion where you have, like they have there, b to the s equals b to the t, where both sides have the same base, right, to some power, base 2. Remember what that property states is that if I see that, then we can just equate the powers. Right, so here's that one-to-one property, written in shorthand up here. So the only way these two are going to be equal is if the powers are equal. So if x minus 1 is equal to 2x minus 4. And we solve the resulting equation and check our solutions. So if I subtract x and add 4, we end up with x equals 3 here. And that's it. Right, and of course check your solution back in the original equation. Left side, you'd have 2 to the 3 minus 1, which is 2 squared. The left side would be 4. And the right side, 2 times 3 is 6, minus 4 is 2. 2 squared is 4. You have 4 equals 4. This works. Now another way you could verify or maybe triple check your work is with a graph of each of these expressions. So I'm going to go to that free online graphing calculator at desmos.com, and in one line I'm going to graph the left side of the equation, y equals 2 raised to the x minus 1 power. Oops, it was the x minus 1 all in the exponent. That expression there. And then the next line I'll graph y equals and then the expression on the other side, 2 raised to the 2x minus 4 power. And then look at where they cross. And you see, the nice thing about Desmos is they'll point out where things cross. And you see they cross at the point 3, 4. So they're going to have the same value, right? Both of these outputs will be 4 when x equals 3. So x equals 3 is our solution. As we saw in my writing here, right? X equals 3. Great, so that's another way to doubly or triply verify your solutions. All right, next example. Same setup. It already looks like this: b to the s equals b to the t, right? Both sides are a single base to a single power, and they're the same base. Both are base 5. So applying this one-to-one property, the only way these two are going to be equal is if the powers are equal. So 2x on the left must be equal to 3x plus 2, the exponent on the right. And then solving for x here, x would be negative 2, right? Subtract 2x, subtract 2, or subtract 3x and then divide by negative 1, whatever. And there you go. And check it, if you were to replace x with negative 2, you'd have 5 to the negative 4 on the left, 5 to the negative 4 on the right. And once again, and this will be the last time I show you this one, but if you go to graph both expressions, the left side and the right side, you can see where they meet, and the x value of where they meet will be the solution of the equation. Right? It was y equals 5 to the 2x power, and y equals, get rid of all this, 5 raised to the 3x plus 2 power. And again, you can see they point out the point where they meet here at negative 2. The output, I'm assuming this is rounded to 3 decimal places here, because the output is 5 to the negative 4th on both sides. Right, that's 1 over 625. That rounds to 0.002. But the x value is what we're looking for. The solution of the equation is negative 2. Makes the output on both sides, the value on both sides, the same. Wonderful. All right, now the next page is a little different, because you see now I have, both sides are a single base to a single power, right? 8 to the x plus 2 power equals, and then 16 to the x plus 1, but they do not have the same base. The left side has a base of 8, the right side has a base of 16. But that's what I was talking about back in the text. They tell you, hey, sometimes you might have to use some rules of exponents, properties of exponents, to rewrite these expressions so that you do have the same base on both sides. Now, 8 and 16 are both powers of 2. So I'm going to rewrite these. So instead of 8 to the x plus 2 power, I'm going to rewrite 8, replace 8 with 2 to the 3rd. Now again, usually when you replace something, put parentheses around it. So instead of 8 to the x plus 2, now I have 2 to the 3rd to the x plus 2 equals. And then same thing with 16. I'm going to replace 16 with 2 to the 4th power. So in parentheses, 2 to the 4th power, that's 16, raised to the x plus 1. And then I'm almost finished. All right, we're not quite there yet. I need to simplify this, get rid of the parentheses using a property of exponents. Now remember, when you raise something to a power, and then that again to another power, you multiply the powers. So this left side would be 2 to the 3 times x plus 2. Now 3 times x plus 2, when you distribute the 3, would be 3x plus 6. Right, you multiply both those terms by 3. And then same thing over here. I have 2 to the 4th, and then to the x plus 1. That would be 2 to the 4 times x plus 1 power. But 4 times x plus 1, after distributing the 4, would be 4x plus 4. And now I have that b to the s equals b to the t form, right, where both sides are a single base to a single power, and the base is the same. They're both base 2. So then I can jump into the use of the one-to-one property and just equate the exponents. So from here, 3x plus 6, the exponent on the left side, must be equal to 4x plus 4, the exponent on the right side. Then subtracting 3x and subtracting 4, I see that x must be 2. And then you can check, is 8 to the 4th power equal to 16 to the 3rd? I mean, absolutely. Both of those would be equivalent to 2 to the 12th. They'd both be 2 to the 12th power. So this does work. And once again, if you wanted to, you could graph the expression as a function on the left. You can graph the expression on the right as a function. And you'll see they'll meet at a point where the x value is 2. Now, you might not see it right away because the output's going to be 2 to the 12th power, so you might have to go up quite high to see where they meet. But where they do meet, the x value will be 2, the number 2. Okay. Next one, same issue. Sure, both sides are a single base to a single power like this, but they're not the same base, right? Base 5 on the left, base 25 on the right. But 25 is a power of 5, right? It is 5 squared. So, like with the last problem, the left side I'll keep as 5 to the 2x power. The right side, I'm going to replace 25 with 5 to the 2nd, right? That replaces the 25, and now I have base 5. And this is being raised to the 3x plus 2 power. And then again, I want to simplify this side, get rid of the parentheses using that power to a power rule for exponents, multiply these. So on the left side, I have 5 to the 2x equals, and then over here, 5 to the 2 times 3x plus 2. When you multiply these, when you distribute the 2, that would be 6x plus 4. All right. And now I have what I want. Now I have a scenario where I can use this one-to-one property. Same base to some power on both sides. So I equate the powers. The 2x is the exponent on the left, must be equal to 6x plus 4 on the right. Then I subtract 6x and divide by negative 4. I would see that x equals negative 1. All right, and there's our solution. And if you want to check, you plug in negative 1, you'd have 5 to the negative 2nd on the left, and then 25 to the negative 1st on the right, which is, they're both 1/25. That's true. They have 1/25 equals 1/25. So this is a valid solution, negative 1 for x. Alright, so I continue this. Alright, the next page has more stuff that I have to manipulate. So in example 5, you see here I have 2 to the 5x power on the left, and then the square root of 2 on the right. Now I hope you recall that a root, square root, cube root, whatever, is a power, a fraction power. All right, the square root of 2 is actually the same thing as 2 to the 1/2 power. And now I have what I want. I have the same base to some power on both sides. So I apply that one-to-one property and equate the powers. So 5x on the left must be equal to 1/2 on the right. And then just simply multiplying both sides by 1/5 or dividing by 5, I get x equals 1/10. And there you go. Pardon me. Okay. And again, check the result, and you'd have 2 to the 1/2 equals the square root of 2. That is correct. Alright, example 6 is a little different. In fact, I don't know why it's part of the exercises here, are the examples, but it is a nice example to point out still. I have 2 to the x equals, negative 100. remember, an exponential function, b to the x. Exponential functions, the basic ones, b to the x, have a range of positive numbers only. So that means this left side, no matter what I plug in for x, is a positive number. But the right side is a negative number. So this will never happen. You can plug in any real number for x you wish, and this will never be true. A positive number will never be equal to a negative number. So this has no real solutions. Or you could say the solution set is the empty set. Now another way you could see this, if you didn't see that, for instance, another way you could see this is, if you were to change this to the equivalent logarithmic form, you would see that x equals the log base 2 of negative 100. And, oh, wait a minute, that's bad. Remember, you can't have a negative number inside a logarithm. We've seen this before, earlier in this chapter. You can only have positive numbers inside a logarithm and get a real number output. Now, if you continue on in math and whatnot, you'll see eventually that this is an imaginary number here, a complex number with an imaginary part. But, this is not real. And since it's not a real number, they say it's undefined in most calculators, then this thing has no solutions, right? No value of x, no real number value of x is going to make this true. And one other way to see this is also with the graphing. If I were to graph both sides as a function, left side y equals 2 to the x, right side y equals negative 100. I mean, you're not seeing it here because I gotta zoom quite a bit out. But you see where the graph of, there's y equals 100 way down here, this purple horizontal line. And y equals 2 to the x is this graph up here, all above the x-axis. They're never touching, right? They're never going to cross each other. So there's no solution. Right? Okay? Great. Alright, so now back to the task at hand, where we have to make sure both sides have the same base. So here I have 4 to the negative 3v minus 2 power equals 4 to the negative v power. So both sides are a single base to a single power, and that base is the same, 4 and 4. So applying that one-to-one property, the exponents must be equal. So negative 3v minus 2 on the left must be equal to negative v on the right. And then if I were to add 3v, then divide by 2, we'd see that v must be negative 1. And there's your solution. And of course, check it out. You plug in negative 1, you'd get 4 equals 4, 4 to the first on both sides, which is working out. Alright, then some more of the same down here. Again, both sides, they're not in this form. Alright, b to the s equals b to the t. So I can't use this property right now. But I can use some properties of exponents to write both sides as, some single base to a single power. Alright, so on the left side here, remember when you multiply things with the same base, you keep that base and add the powers. 2x plus 1 plus x would be 3x plus 1. And then on the right side, 243 is 3 to the 5th power. 3 to the 4th is 81 times 3 again would be 243. All right, now I have what I want. B to the s equals b to the t. They both have base 3 to some power. I can apply that 1-to-1 property and equate the powers. 3x plus 1 equals 5. Then I subtract 1, divide by 3. X would have to be positive 4/3. All right, positive 4/3. All right, and once again, if you check it out or graph stuff and see where they meet, the x coordinate of the point where they meet should be 1 1/3 or 1.3 repeating. But I'll leave it to you to check that stuff out from here on out. Great. All right, my final page is again more of the same, where both sides, aren't in that b to the s equals b to the t form, single base to a single power. But I can use, the nice thing is all the bases can be written as the same base. And I can use properties of exponents to get it that way. Now, 625 is 5 to the 4th power. Now, I'm going to try to write everything in base 5 here. So 625 is 5 to the 4th times 5 to the 3x plus 3 equals, and then 125 is 5 to the 3rd power. And then over here, you can do that product property again for exponents. When you multiply things with the same base, you keep that base, and the exponent is the sum of the exponents. 4 plus 3x plus 3 would be 3x plus 7. Pardon me. And then I still have, just 5 to the 3rd on the other side. And now I have what I want, right? Both sides have the same base to some power. I then equate the powers, right, using that 1-to-1 property. So 3x plus 7 must be equal to 3. Subtract 7, divide by 3. X here, the solution would be negative 4/3. And again, I'll leave it to you to check that out. Plug in negative 4/3 for x. And the left side value should be the same as 125. All right, and then more of the same in the last example. Now I'm noticing the bases here are 2 and 8 and 1/64. These are all nice powers of 2. So I'm going to try to write everything here as a power of 2, base 2. Now 64, right, 2 to the 6th power is 64. But this is 1/64. So that's the same thing as 2 to the negative 6th power. Right, that would be 1/64. So I'm replacing 1/64 with 2 to the negative 6, and this again is being raised to the 3 times n, times 8. 8 is 2 to the 3rd power. And then the other side is already the way I want it, as base 2 to some power. Now, using properties of exponents, this power to a power rule, you multiply these. So this would be 2 to the negative 6 times 3n would be negative 18n power, times 2 to the 3rd equals 2 to the 6th. And then once again, I have a line where I can use the product rule for exponents. You multiply things with the same base, then those powers get added. So this is 2 to the negative 18n plus 3 power equals 2 to the 6th. And now I have what I want to be able to apply the 1-to-1 property. Both sides are the same base to some power. So the exponents must be the same. Negative 18n plus 3 must be equal to 6. And then I subtract 3, I'd get 3 over here divided by negative 18. N would be negative 3/18 or 1/6. And there we go. And again, don't forget to check it out. Plug in negative 1/6 here. That'd be this to the negative 1/2, which would be 8, and then times 8 is 64, which is the same as 2 to the 6. So this works, negative 1/6 for n. Alright, and that's all. So again, I'm assuming here you know your properties of exponents. And now also that one-to-one property for exponents, so that when you have a b to the s equals b to the t, s must be equal to t. Then you can equate the exponents, solve the resulting equation, and check your solution back in the original equation, of course. Okay, great. And I'm hoping that watching me go through these 10 examples here helps you in some way when you are asked to use like bases to solve exponential equations on your own. Thank you very much for watching.